Hello and welcome to Big Ideas Only. This podcast is brought to you by Montanus, a company specialized in creating high-quality content for marketing departments in mostly knowledge-driven companies. I'm Mikkel Svold, and in this second episode, we'll look into what the sun has to do with the climate on Earth. And I know this sounds rather obvious, but before you leave, let me tell you, there's more to it than you think, and apparently it's a pretty complex matter. So to understand the true complexity of the relationship between the sun and the climate and Earth, I've invited Christoffer Karoff into the studio. Welcome, Christoffer.
Thank you.
Christoffer is an associate professor of astronomy, physics, and geoscience at Aarhus University in Denmark, and is currently researching on the evolution of stars, planetary systems, as well as the activity of the sun. Now, I need to understand, is Earth just that lonely planet? I guess not lonely, but is it just dangling alone in the universe, completely detached from everything else as long as you're outside of the atmosphere? I know, of course, the sun has some influence, but is it mainly that alone globe hanging in the void?
No, it's definitely not in the void. and I mean, of course, when we look at the sky, we see the moon and the sun, and that they are sort of the first thing that make us realize that we are not alone. And the moon has a big effect on us here on Earth, and so does the sun, of course. I mean, we can try to turn it off for a bit, and then we would realize that not much would go out without the sun here. Then we have the other planets in the solar system that sort of affect us a little bit, but not too much. But then we actually also have the galaxy. So I mean, the whole solar system is traveling inside the Milky Way, or rotating around in the Milky Way.
But does that have an effect on Earth?
Yes, but on a longer time scale, it has an effect. So
I'm sorry for the noise in the background. We have someone drilling a hole in the wall next to. I don't know, but sorry.
Yes. So I mean, first of all, I mean, the solar system was made out of the galaxy. So without the galaxy, the solar system would not be made. And then we have a bombardment of what we call cosmic particles from the galaxy that is likely to have affected us, at least in the past. Sort of when stars go supernova around us, they shoot a lot of these cosmic particles towards us.
And we're talking particle size. We're not talking asteroids and...
No. We're talking particle size.
Actual particle size.
Yes.
Yeah.
And I mean, that have probably evolved, have affected the evolution of life on Earth.
Will the galaxy affect life on Earth or Earth into the future as well? You say that it certainly has done.
Yes, it definitely will again, but the time scale is extremely long here.
Okay.
So I mean, I guess we tend to think that we see as a nearby supernova every 1,000 years or something like that, and it has to be very nearby to actually affect us. So I think the time scale for these close nearby supernovas is sort of some million of years, and probably.
Okay. I
mean, it's 60 years since the dinosaur died, so I think that's sort of the time scale. But if you look at that on the Earth time scale of 4,500 million years, then it actually, I mean, then we experience a few of those, which probably have affected us. So it's not something that are important for us as we sit here now, but it's important.
We shouldn't be nervous.
No, but It's important when you want to understand the evolution of the Earth and of life on Earth.
And if we look into a little more the closer proximity to Earth right now, so right now obviously there's a lot of talk about the climate and hopefully also a lot of action, but how does the nearby, so the moon but also the sun, how does that affect the climate? I know that the sun warms up and cools down when it's not pointing directly at us, or when we're not pointing directly at it.
So I mean, let's try to wait with how it affects us now, because I mean we know a lot more about how it affected us in the past. And for example, if just after the Earth was formed and the Sun was formed, there was too much what we call short wavelength radiation, so very energetic radiation from the sun, X-ray and gamma radiation, to allow life to form on Earth. So I mean, we are very confident that life did not evolve for the first 500 million
Simply
years.
because it was radioactive.
Yes.
Yeah.
So that we know. So the sun had to sort of cool down. I mean, not temperature-wise, but with these very energetic radiation that comes from the sun, and particles actually also. Then the Earth orbit around the sun is not a perfect cycle. It's ellipse. And the form of the ellipse and the configuration of the Earth and the Sun in that ellipse changes on timescales of between 20,000 years and a few 100,000 years. We believe that that's one of the main drivers of the ice ages that we have experienced here on Earth.
Say that again. So the ellipse that when we're circling around the Sun once every year, the shape of that ellipse is changing.
Yes.
So it's bigger. Is the shape that's the same, or is it becoming bigger or smaller, or is it like deviating into some other kind of ellipse or circle?
It's a bit hard to explain only with words, but I guess there are cameras here. So I mean, we have the Earth's ellipse around the sun, and then we have the sun sitting actually in one side. Then the first thing is that I mean, the Earth rotation axis is not completely perpendicular to the orbit around the sun. It's a little bit tilted with 22 degrees.
Yeah.
And that tilt changes.
Those are the seasons, right?
Yes. So the tilt caused the seasons.
Yeah.
But the seasons changed on a timescale of 20,000 years. And that means that the length of the seasons changed. And that we believe is one of the main drivers of ice ages.
And it's every 20,000 to 100,000 years.
So
it's not something that we will feel, when old people say, "Oh, back in the days it was always 2 meters of snow." That's that's not it.
Yeah. and we are now, I mean, it's 20,000 years since the last ice age, and actually we don't expect a new ice age to be coming in the first few thousand years.
Okay.
So it's not a. The problem is that you have at least 3 strong signals here, and when you couple them together, you lose these very strict periodic cycles of 20,000 years. So on average, it's 20,000 years, but the one we are in now is not going to be 20,000 years.
Also, just deviating with 1,000 years, that's also going to be quite a huge thing for us today sitting here.
Yeah, but the change in the Earth rotation axis is very, very periodic. So that's 20,000 years. Then you have the change in sort of how much an ellipse there is Earth's orbit around the sun is, and how much is a perfect cycle, and that has a longer time scale. That's the 200,000 years time scale.
Okay.
And you have 2 differences in the rotation period. I mean, it's and now I saw I lacked the English word, a snore top. So these things that you used as a kid that you could spin around. When you start such thing, it will spin around itself.
Yeah.
But it will also make this wobbling, slowly moving thing, and that's actually what we see with the Earth rotation. That is, it's spinning with one orbit a day, but then it's making this wobbly movement every 20,000 years, which is sort of well understood, but the period is there.
And then again, coming back, okay, so we have these changes in the Earth's orbit and also the tilt.
Yes.
How does that affect climate today? And is it something that's measurable or at least understandable? Or do we need to go back all the way back to the Ice Age?
We need to go back to the Ice Age because
to understand the
change,
difference today.
Because the change is so slow.
Yeah.
And we think that we have a reasonable understanding of it, and can be able to predict that in the future the climate, but in the future 1,000 of years the climate will be colder. So it's not going to solve our problem with global warming. And I mean, If we don't do anything to global warming, the amplitude of this will be insignificant to the temperature decrease that we are about to witness. But if we left things as they were before we start using fossil fuels, then we would, in a few thousand years into the future, move into a new ice age. Yes.
Wow. So we know. Yeah. So basically, we know that it's coming. And is there any what can the sun and the activity at the sun right now, or in these years, what do we know about that and climate on Earth?
Yes. So now we move closer up to today and on a shorter time scale. And you already now introduced this word activity of the sun, which is
I saw that in my research. I think you used it somewhere.
Yes. and it's a very strange term, and we often don't agree on what we mean, but it's something related to the magnetic field of the sun. And the magnetic field of the sun changes on actually 22 years time scale. But the other thing that changes is these spots that we see on the surface of the sun from time to time.
And what is that?
Yeah, that's okay. That's also a good question, and that's I think we have an understanding of it now, but it have actually been hard to figure out. So today we believe that it's magnetic field penetrating the surface of the sun, but normally you would not be able to see a magnetic field because magnetic fields are invisible. But what happens is that the magnetic field makes the energy transport from the interior of the sun out to the surface less efficient.
Okay.
And so when you have the magnetic field penetrating the solar surface, less energy escapes the sun at that exact place.
Which makes it visible from Earth.
Yes,
so
and
if you take a binocular or a telescope and look at the sun, you would be able to actually see like a color difference.
Yes, yes.
Don't do that at home, by the way.
No, actually, so of course, don't do it through binoculars. Then you go blind immediately. When we had solar eclipses, we had these sunglasses that special made sunglasses, and if you're lucky these days, you can actually go out and look at the sun with them and be lucky to see spots on the surface these days, because we are right now experiencing some of very big spots on the sun.
Oh, really?
That's it's just about possible to see with the human eye. It actually depends on how large your eye is. So people with small eye can't see them. People with big eyes can see them.
For real?
So, yes. So,
that's so funny.
Yes, and I guess so. Sunspot is sort of close to our definition of what we call solar activity. But sometimes you need to be a bit more precise with what you're talking about, because the sunspot will of course not affect the Earth climate. It has to be something else. But we see, when we look back in time, a rather strong correlation between the sunspot number and the climate on Earth. So it really indicates that there's a strong connection there. And
so a single sunspot doesn't make a difference, but if we have a lot of them.
Yes. But we don't know why. And so that's actually the interesting question, and people have been looking into this for the last. Actually, I believe it was a Danish astronomer who first suggested this in 1758, called Christian Hobro, who was the director of Rundetårn. So for the last 200 something years. We have been looking into, can these sunspots actually affect the climate on Earth, and how? The first way you would imagine them to affect the climate here on Earth would be that if you have this brilliant sun shining with a lot of energy, and then you place dark spot on the surface of it, then you would receive less energy from the sun. But the problem is that it's the other effect we see, that when there are many spots on the surface of the sun, it actually gets warmer than when there are less spots.
Okay.
So that was sort of the first problem to try to understand.
That is a problem.
But then people tried to measure. So what is actually the change in the brightness of the sun over these 11-year sunspot cycles, where we have many spots and few spots? And they came out with all sort of results. Another thing that you can do in astronomy, so when you measure the brightness of the sun, it of course depends on how bright it is at a given place, but it also depends on the size. So if you somehow could increase the size of the sun a little bit, it would also shine more. So people also looked into actually determine how big the sun was, and couldn't agree on it. And then in the late 70s, we had the satellites starting to come up, and had high hope that would sort of help us solve that question, because the problem is when you observe from the surface of the Earth, you have observed through the atmosphere, which is filled with water, and these water droplets disturb the signal. I mean, they actually act as small lenses. But to begin with, that didn't work either. I mean, because you had one satellite coming up with one value for how much energy we receive from the sun, and then you had another satellite coming up with one that was, 20-30% off.
And why is that?
Well, the problem is to measure the brightness of the sun, you cannot compare it to anything, because when you look up, there's nothing in the sky as bright as the sun. So you have to do it in an absolute way. On a satellite, where you have a problem with calibrating your instrument, and so these instrument that you launches on a satellite pretty fast degenerate, so they becomes less efficient, and therefore, you need to know exactly how efficient it is, but there's nothing you can use for that, because
because you don't have another sun to compare it with.
Yes.
You need to compare it up against the efficiency of the measuring instrument.
Yes.
Yeah.
So it was first when we've had a lot of satellites actually trying to do this, that we were able to sort of calibrate them against each other. And I would still say that the absolute level of the energy that we receive from the sun is uncertain with 10-20%.
And you couldn't just use the same satellite to measure twice in a row?
No, because it degenerates all the time, so it becomes less efficient. So if you have a satellite observing the sun for
because the observation should be 5 or 11 or 22 years later.
Yes.
So
yes.
Yeah, okay, that makes sense.
But then we saw it, and then we actually saw that when you have many spots on the surface of the sun actually becomes a little bit brighter, as we saw with this correlation with climate. But the change was so small. It's only 0.1%. The sun's brightness is changing, and before I talked about uncertainty on the single measurement of 10-20% or something like that. So we're really digging down to the details here, and people do not completely agree on these results, but yeah, okay. I would go would say 0.1% for the last 40 years or something like that.
And does that have a significant impact on Earth?
No. That's very hard to explain any significant impact on sort of global warming. Now the reason why the sun can actually go brighter when you put spots on it is because apparently the energy have to get out anyhow. So if you at some place on the sun's surface place a strong magnetic field, which makes that part of the sun less efficient in transporting energy, the energy just escapes somewhere else. So it doesn't block the energy from coming out. It's just
pressure on some.
Yes.
Yeah.
And then you have other places where you have weaker magnetic fields that do not generate dark spots, but they make another phenomenon that they actually change sort of the we call it the opacity of the sun, the transparency of the sun. So where we have weaker magnetic field, it actually means that we look a little bit into the sun. Now, nothing is a little bit when you're up at the sun, so it's still a few hundred kilometers more into the sun that you look, and there it's a little bit hotter, and therefore these areas becomes a little bit brighter. We call them facula, and then they're very hard to see on the sun with a telescope. But if you know what to look for, you can see them sort of close to the limb as sort of diffuse white regions, and so on a daily basis. the sunspot dominates the variability we see from the sun. But when we look into these decadal, so 10 years time scale, these facular things actually dominate, and therefore over a cycle, the sun is a little bit more bright when there are strong magnetic fields. So when there are many sunspots. But the effect is too small to have an effect on climate.
Yeah, so it still doesn't excuse that you know.
But the other thing is that I mean, we have only observed this since, okay, let's say, I think 1977 when the first satellite up.
Okay.
The first year are a bit dodgy. But we don't have any observation before that. So we can actually only say that the change have been less than 0.1% for the last 40, 50 years. If we go further back in time, we don't know it. I mean, the simplest...
And you can't estimate.
Well, the simplest assumption would be to say that it's the same as today. But of course, you should be careful with that assumption. So there are people who think that, I mean, if you try to reconstruct this back in time using, for example, the sunspot numbers that we have been observing for more than 400 years, or using... what we call cosmogenic isotopes, where we look at tree rings and stuff like that, they suggest that sort of in the 17th century, the sun would have been 0.5% fainter than today. And that would have had an effect on the climate. Sort of that could explain some of the increase in temperature we have seen in the last 200 years. But there's no agreement on that, and I still think that until you have proven it better than you have today, we have to go with the most simple assumption and say that the sun
is going to be the same,
has behaved in the past few hundred years the same as we have observed for the last 50 years.
Wow. Okay, so I want to change the subject a little bit into what can we do on Earth today to prevent the globe from getting hotter in terms of what can we do to the sun? Can we do anything right now? Are there any technologies that can kind of cool down Earth a little bit?
Yes, sure. I mean, we have loads of them. We're not really allowed to use them, but they are actually getting studied pretty serious. I mean, so yes, people are realizing that if we go into a global warming of more than 2% by the end of the century, we will be in trouble. And actually, models predict now that the pace as which we are changing our policies, if that continues, then we will see increase. Then we are likely to see increase in temperature that's much larger than 2 degrees.
Okay.
So is there something else we can do? And I think the first thing is to try to take CO2 out of the atmosphere. That's pretty harmless. So you simply have a machinery that they're building that.
But it's also very inefficient.
Yeah, they're building it in Iceland now.
Yeah, I read an article in, I think it was the Wired magazine.
Yeah, so you need a reasonable amount of energy for doing that, and then you need a place to store the CO2 afterwards. In Iceland, they actually have both. So that's one thing they're trying. And I mean, if you succeed, it's great. If you don't, and it appears that the CO2 is coming up again, well, I mean, you tried. Then I mean, people in Iceland are worried that this will lead to earthquakes. So I mean, what you're doing is that you're pumping water with CO2 down into the ground, similar to what you are doing, or what you are still doing in the US when you look for natural gas with this fracking method. So it actually caused micro earthquakes, and so in Germany it have been that made a law that this is not going to be legal to do on German land. And so they're looking at doing it in the North Sea. So are we actually. So we don't have a law against it, but we're looking at doing it in the North Sea. But of course, what you could also think about is blocking some of the light from the sun. And so it's a relatively small number. So if you block 0.5% of the light from the sun, then we are home safe. So
0.5%.
0.5%.
Okay.
That would be all it would take. And I mean, you can think about many ways to do that. I mean, simply to put up a sun shield that would be, I mean, sort of blocking some of the light from the sun towards Earth. You would probably need sort of a fleet of satellites. But I mean, given that the consequences are temperature increase of let's say 5 degrees would have, then you have a lot of resources to work with.
Yeah, but only if the nations and the states can agree on putting this into action, right?
Yes.
Because typically the richer states, they're not as affected by climate change, or they can easily adapt, whereas the poorer places have a harder time, like in general terms, I guess.
I sort of would tend to believe that if we gotta go with this, then people would do it within a very short time. I mean, we have the technology for doing it, and it's not gonna be insanely expensive.
Okay.
So
how would you do it? What is the technology then?
Launch a lot of satellites with some kind of inflatable sun shield that would take away a little bit of the sun could be one goal. Another one is to try to have some ships, electric ships, that simply just sprayed ocean water up to the atmosphere. So that's called sea sprayed.
Okay.
And that would likely cause extra cloud to come up, and therefore less sunlight to come in.
And will that be a permanent installation that we would need to have, or is it something that should go on for a period of time and then it will kind of run itself at a point?
No, it would likely be permanent.
Okay.
And of course, I mean, if we increase to pump CO2 into the atmosphere, we would have to make it bigger. But I guess, I mean, yeah. I think anyway,
it doesn't actually remove the root cause of the problem.
No,
right. That's the big deal about this. Yeah.
But also that there are many, I mean, aspects that we don't know how it will affect life on Earth. We don't know how animals will react to sort of extasiate on how the atmosphere would react on a longer term to us starting to spray ocean water up to the atmosphere.
And it's irreversible once you've tried.
We don't know that either.
No.
But it could be, yes.
Yeah.
So actually the EU is starting to give out significant money to investigate this, to understand the consequences of these, we call them geoengineering initiatives. So, I mean, and that, I mean, that's, I see this as a change. I mean, we have talked about this for a long time, but sort of started coming up 15 years ago, and now we actually see the government or the EU going in and putting money into initiatives to actually look at this more serious than what we've done so far.
Is it enough, or is it just we put some money over here because then we can kind of pat our back?
I mean, so what they do now is that they put money in to investigate the consequences, so we can start to take a discussion about if we should do it or not. So we're not a state where we're sort of going to do this. We need to discuss it first, and of course we need to have better. The reasoning is that we need to have a better analysis of this before we start. So, of course, you could always use more money, but I think this is. I mean, it's the discussion we need rather than the money. And I'm sure that if we decide to do this, that it's not going to be the money that's the problem. I mean, it's so much more expensive to build these windmill parks to change our agriculture sector to lower carbon. I mean, so I mean, they would be happy to pay for it if they don't have to then cut down the CO2 emissions. So
you actually have something that could be funded by, say, the oil industry or agricultural.
I mean, that's what we're going to do with this CO2 tax that is being negotiated now. That the idea is that you would tax all private companies, with I think it's now €100 per ton of CO2 they emit, and that money should sort of go back to combating this. And if you put those money into developing these geoengineering initiatives, then I think no problem. I mean, you would, yeah.
Okay. Yeah.
So, but it's as you say, it's not dealing the roots, dealing with the roots. It's dealing with the symptoms, and that's probably why people are reluctant enough to do it. So.
Yeah. Before we end, I think I want to know a little bit about what you're researching on right now.
Yes. So I said this thing about trying to understand how the sun then affect our climate here on Earth, and I mean, one thing that we realized. But a number of researchers in the world, the community realized, let's say 15 years ago or something like that, was that if we are to understand it, we cannot look at a global scale. We have to look at a regional scale. So we have worked a lot on understanding actually how the sun influenced our climate here in Scandinavia and Northern Europe, and we have actually come quite far there. So. I mean, and I know this sounds a little bit sort of punchline, but the sun is the main cause of whether we get white Christmas in Denmark or not. So the sun is clearly the main driver of the winter climate here in Scandinavia and England and Northern Europe. So we can see when there are no spots on the sun, then we have a lot higher tendency for having a cold winter. So if we
and it's a more important driver than, say, ocean currents or
yes. So if you were to predict one thing that you could know for predicting the winter climate, you should take the sun, and that's because I mean We think we understand it, but it's because that this small change in the brightness of the sun, I mean, it doesn't warm up the whole globe, but it changes the weather patterns.
Okay.
So normally we have in the wintertime we have this mild air coming in from west with rain and temperatures around zero, and these storms from time to time. But then, sometime when the sun is a very low activity level, we can get into another state where we have cold wind coming down from northeast. That's when we talk about that. We get the Siberian cooling down to us, and then it can get locked there, and we have experienced that a few winters, and the sort of the risk or chance, if you want, of the climate system getting locked in the Siberian winter cold here in Scandinavia is much bigger when we have low solar activity. So that's one thing where we have made some progress. The other thing that we're looking at is that, I mean, we have a number of climate drivers, and we talked about CO2 and we have talked about the sun, but we also have volcanoes. And I mean, again, if we look back in time, we can see that volcanoes are major climate drivers. So that when we have the big volcanoes going off, then the temperature drops the next 5 years.
Just to briefly touch on that, that's because it shoots a lot of ash into the atmosphere, which basically does what you just talked about, blocking the sun. Yes. So that creates that layer of...
Yes. Yeah. And after a period of 5 years, something like
it's
that,
all fallen down again.
It's fallen down again.
Okay, yeah.
But so the idea is that it can be that but it's changing sort of the chemistry of the atmosphere, and so that can affect how the atmosphere is affected by the sun. So if we are to understand how the sun affects the atmosphere, we have to understand how the volcanoes affect the atmosphere at the same time. So that we have to understand both, and actually then also include CO2 at the same time. CO2 is a bit more easy. I mean, we have a pretty good understanding on how CO2 affects the atmosphere, so that's the easy part here.
Okay. Now, our time is nearly up. But if the listeners, they want to learn more about your research and I guess research on the subject in general, where would you recommend they go?
So there's this webpage called videnskab.dk, who often takes up this history, and they have sort of branched out the climate debate into a Facebook page called Red Verden, which is sometimes interesting to look at with some heated discussion, but there's often a lot of information about this.
And I guess NASA's website is also often a good place to go.
Yes, but that's incredibly big, so you have to know where to look. NASA has a satellite that went up in 2009 called Solar Dynamic Observatory, or it's in daily life it's called SDO. So if you Google NASA and SDO, then you come to a webpage with a lot of daily or hourly updated images of the sun in beautiful colors.
And what if we want to look into your research? Where should we look?
I think this videnskab.dk is often where it sort of comes out in a more popular form than the scientific.
Otherwise,
papers.
You could go to Aarhus University's website and probably find links
I guess
to the research papers.
we could be better for doing that. I also have a column on the backside of a Danish newspaper called Kristi Dagsblad, together with Tina Ibsen. So from time to time I write there, mainly actually about the sky, but often I'm able to put in a little bit about the climate too. So.
Sneak it in. Okay, thank you so much. All right, Christoffer Karoff, thank you so much for coming. And to you, dear listener, if you like this podcast, please help spreading it by subscribing and sharing it with your friends and family. And of course, you can find the show notes with links to everything we've talked about on our website, which is montanus.co/bigideasonly. And that's it for now. Thank you so much for listening.